Okay, let's just forget about code, forget about the cloud for just a minute. Have you ever wondered what the actual physical foundation of our digital world is? I mean, what is it made of? Today, we're going to dive into the incredible journey of creating the single most fundamental ingredient of all modern technology. We're talking about a material so perfect, it basically pushes the limits of science itself.
All right, I want to start with just a number, $100,000. Now, what's that the price of? That is the price for a single 300-millimeter disc of silicon.
Yeah.
100 grand. So why? I mean, how on earth can this one seemingly simple wafer be worth more than a luxury car?
Well, the short answer is, there is absolutely nothing simple about it. That staggering price tag, it comes from one of the most precise, most demanding manufacturing processes on the entire planet. We're talking about a journey that pushes the very limits of what's possible in engineering and purity.
And look, I know that sounds like an exaggeration, but it's really not. From the smartphone that's probably in your pocket right now, to the massive supercomputers running our global infrastructure, our entire digital world is built on these flawless, fragile little disks. They are, quite literally, the bedrock of all modern tech.
But what's truly mind-boggling is where this whole journey begins. You'd think it's in some sterile, high-tech lab, right? Nope. It starts with something you could literally find on the ground. This whole journey to perfection, it starts with just a common, ordinary rock.
So how do you get from a humble rock to that $100,000 wafer? Well, the material has to pass through what you could call 5 distinct trials. First, it's mined and crushed. Then it's smelted and refined. After that, it's purified to an absolutely incredible degree, grown into a single perfect crystal, and finally, it's sliced and polished to near atomic perfection. It's quite a gauntlet.
Okay, so that first step is all about sheer force. We take this rock, quartzite, and we smelt it in a massively powerful arc furnace. What comes out is something called metallurgical-grade silicon. Now, it's about 98% pure, which sounds pretty good, right? And yeah, it's useful for making stuff like aluminum alloys, but for the world of microchips, it's still hopelessly contaminated.
And that brings us to what I like to call the purity gauntlet. This next stage, this is where the real challenge begins. This is where we start pushing chemistry and engineering to their absolute extremes.
So the goal here is, it's almost hard to comprehend. You have to remove nearly every single non-silicon atom from the material. Think about it. Even one stray atom can act like a giant boulder in a tiny stream. It completely disrupts the flow of electrons and can ruin a multi-million-dollar chip. We're talking about a level of perfection that is it's really hard to wrap your head around.
And that brings us to the target number. To be considered electronic grade, silicon has to be refined to at least, get this, 99.9999999% purity. People in the industry call it 9 nines purity. Let me put that in perspective for you. It means for every billion silicon atoms, you're allowed only one single impurity atom. That's it. This makes it one of the purest materials ever created by humans, period.
But being ridiculously pure isn't enough. Nope. Now we have to take this incredibly pure molten silicon and do something that, honestly, sounds like it's straight out of science fiction. We have to grow a single, perfect crystal from it.
And here's the key concept you need to know. Monocrystalline. All that means is that the atomic structure is perfectly ordered. It's continuous and unbroken from one end to the other. There are no seams, no grain boundaries, nothing. And that perfect structure is what allows electrons to flow predictably. And you absolutely need that if you're going to create billions of reliable transistors on a single chip.
So how do they do it? The process is called the C-Trokarovsky method. It's pretty amazing. First, you melt all that pure silicon in a big container, a crucible. Then, you dip a tiny, perfect seed crystal right into the surface of the molten liquid. And then, very slowly, very painstakingly, you pull that seed crystal upwards while rotating it. As it's pulled up, the molten silicon just latches on, cools down, and arranges its atoms to perfectly match the seed crystal's flawless structure. It's like magic.
And the result of this incredibly meticulous process? It's this massive, perfectly formed monocrystalline ingot. Sometimes these things weigh over 100 kilograms. That's more than 220 pounds. And it's one continuous, flawless crystal from top to bottom. It is a true marvel of material science.
Okay, so we have our perfect ingot. But how do we get from this giant cylinder to those ultra-thin disks we talked about? Well, this brings us to the final and maybe the most delicate stage of all, slicing it all down to atomic perfection.
This is where it gets crazy precise. They use diamond-edged saws to slice that ingot into wafers, and each one is thinner than a human hair. But even that's not good enough. These rough slices are then lapped and polished with special chemicals until they have a surface like a perfect mirror, so smooth that any leftover imperfections are measured in single atoms. It's an almost impossibly precise process.
And really, that just perfectly summarizes the entire incredible transformation we've been talking about. Think about it. We started with a common rock, something you could literally just pick up on a hike, and we ended with a manufactured surface so flawlessly flat and so pure that it pushes our ability to even measure its perfection. It's just wild. So, the next time you pick up your phone or you use your computer, just for a second, think about that journey that started with a rock. If our entire digital civilization really is built on these perfect, fragile little disks, and it's dependent on one of the most complex supply chains ever created, what does that fragility mean for our future? It's something to think about.